Hi folks, this is Vivek from ExamVictor. In this lesson I'd like to deal with problems with cubes. And as usual, if there are any comments or any feedback, any thoughts on this lesson, please do send me an email at vivek@examvictor.com. So cube problems are not necessarily dealing with the cubes of numbers. They're actually dealing with physical cubes. Mostly you'll be given a lot of manipulations that happen to these cubes. They'll be cut, they'll be painted, colored, sliced. You would have to figure out how many cuts are needed, how many sides are painted, what is written on the other side, etc. So clearly 3D visualization skills are a real boost, a real help here. But if you can draw a diagram, just a quick neat cube diagram, that helps as well. If you can just quickly draw up a cube and then start writing sides and measurements on it, that helps. There's also some basic math involved, which we'll see on the next page. Okay, so let's now consider a very simple cube. Let's say the cube has side S, right? So each side of the cube, all sides are equal and the side is S. So then some things are very obvious. The volume is S cube. The surface area is 6S square because there are 6 faces. Each face has the area of S square. So you have 4 faces on the sides, 1 front, 1 back. So totally 6S square. We just counted, so 6 faces. How many edges? So each face has 4 edges. So if you look at the front face, you have 4 edges. 1, 2, 3, 4. Similarly, the back face has 4 edges. And then you have 4 edges connecting the front and the back. So that's 4 into 3, 12 edges. The face diagonal, which is this diagonal of the cube. So this is a right angle triangle of each side S. So the hypotenuse is root 2S. So S root 2. That is the face diagonal. How about the body diagonal? The body diagonal is the one that connects, say, this vertex to this vertex. Right? This is inside the cube. This is the body diagonal of the cube. So for the body diagonal, it's also a right triangle. But now, one side is the face diagonal itself. So that's S root 2. And the other side is this one, S. So this is, if you look at this, the hypotenuse of this is actually S root 3. So S root 3 is the body diagonal. Right. So with those basics, let's look at a few example problems and it will become clearer. Cube problems are not really that hard. The only thing that they require is some visualization. So this first question says, a cube of side 6 centimeters has been cut into 64 smaller but identical cubes. It was estimated that 4 liters of paint were needed for the 6 centimeter cube. Then how much paint is needed for all the faces of the smaller cubes? So there was a large cube and it had side of 6 centimeters. And this has now been cut into lots of smaller cubes. Right? 64 of them actually. So first things first, the volume of this large cube, this is 6 cube. Right? And the volume of the smaller cube we don't know, but we do know that each smaller cube is going to be 1/64 or 1 by 64 of the large cube. So the volume of each smaller cube is going to be 6 cube by 64. Right? So now that we know the volume of the smaller cube, we can find the side of the smaller cube. The side of small cube is equal to the cube root of 6 cube by 64. How much is that? So 64 is 4 cube. So this is actually the cube root of 6 cube by 4 cube. So it's actually equal to 6 by 4 or 3 by 2. So now that we have the side of the smaller cube, I'm just going to clear up some space. Now that we have the side of the smaller cube, we can now start calculating the surface area. So side equal to 3 by 2. So surface area again of the smaller one is equal to 6 into 3 by 2 square. We know that the surface area of the larger one is equal to 6 into 6 square, which is equal to 6 cube. Right, 6s square. I'm just applying the formula 6s square. Now, this surface area requires 4 liters. this is the surface area of one small cube. How much paint would 64 of these require? That's the question. So it's a simple ratio and proportion now. 6 cube requires 4 liters. So 64 into 6 into 3 by 2 whole square requires what? And now you just have to solve this ratio and proportion. Again, I'll clear up some space here. Once you do the math, it's very simple, I'll walk you through it. Once you do the math, this just comes out to 4 into 64 into 6 into 3 square by 4 by 6 cube, right? That's what this missing term is. So just cancel off stuff. This is 6 square, and 6 square can be written as 3 square into 2 square. 3 square cancels. This is 16. So the answer, all this, is 16. So the answer would be D, 16 liters. If you didn't follow the calculation, just try them again yourself. Very simple and won't take much time. The principle that we really used here repeatedly was the volume and the surface area. Volume is S cube and the surface area is 6S square. So as you saw, basic formula are all you need for cubes. Okay, another example. This is an interesting one that talks about the number of cuts. So before we get into the weeds and start solving the question, just the basic principle. If you make n cuts along a cube, then you'll get n plus 1 pieces. Very simple. If you just look at a normal, if I just take a rod, right? It's in one dimension, it's just a rod. And if I make 3 cuts, 2 and 3, I actually get 4 pieces, right? I get this piece, second piece, third piece and fourth piece. So that's what I'm trying to say. I'm extending that concept here. I'm saying that n cuts gives me n plus 1 pieces. And the thing is that this is n cuts per axis, right? So if let's say I make n cuts in one axis and I make m cuts in the second axis, and let's say I make l cuts in the third axis, then the thing is the number of pieces that I get are n plus 1 into m plus 1 into l plus 1. This is the total number of pieces I get by making those number of cuts. Now, the question is asking what is the least number of cuts required to cut a cube into 24 identical pieces. So, let's say the number of cuts that I made are n, m and l. Then this into this into this should be equal to 24. Now, it's just a question of solving for n, m and l under the constraints that all three are natural numbers. In fact, they're whole numbers. And I want to minimize n, m and l, right? I want to minimize those numbers. I want to keep them as low as possible. Now 24 is equal to basically 2 into 2 into 2 into 3, right? 8 into 3. So 2 into 2 into 2 into 3. So if I choose n to be 4, m to be 3 and l to be 2, sorry, actually not this, but the whole number, n plus 1 to be 4, m plus 1 to be 3 and l plus 1 to be 2, then 4 into 3 is 12 into 2 is 24, so this works. Also, this is the lowest numbers I could choose and still reach the total of 24. If that is the case, then n equal to 3, m equal to 2, l equal to 1. And n plus m plus l, that's going to be 6. So that's my answer. Why is it not anything else? You can try by trial and error. You'll see that there's no other combination possible that gives you a lower total. Okay, another very interesting one. The question says 125 small but identical cubes are put together to form a large cube. This larger cube is now painted on all 6 faces. So first let's understand what's happening. There are some small cubes and there are 125 of these. And they're all stacked together to form one large cube. Right? Now this cube is made of these smaller cubes. Right? It's just those small cubes stacked together. So actually if you look in detail, you'll see that each side is made up of small cubes like this. Right, that's what you'll see. You'll see that each side is made up of small cubes. Can you say how many cubes actually per side? Yes, you can, because you're told 125 and these are all cubes. So the larger thing is also a cube. So 125 is actually 5 cube. So you know that there are going to be 5 cubes on each side, 5 cubes. So this is extremely helpful for us. Now that we know how the structure is made, that it's made up of 5 cubes on each side, 5 on this side, 5 on that side. So the first question is asking, how many of the smaller cubes have no face painted at all? So the exteriors of this large cube have been painted. So any cube that is on the outside has at least one face painted. So we need to strip off the entire outer layer and see that how many cubes are left. Now if you look at any one face, just look at one face of this cube, the larger cube. The side is 5 and it's made up of 5 small cubes, right? Each side is made up of 5. Similarly, this one is made up of 1, 2, 3, 4, 5 cubes. Now, all of these outer cubes have paint on them. Similarly, the whole line, the whole perimeter, all the cubes have paint on them. The ones that don't have paint on them are on the inside. What will the side of that inside cube be? That is going to be 5 minus 1, because 1 from this side and 1 from this side. So 1 here, similarly 1 here and 1 here. So the side of this inside square of the face is going to be equal to 3. So for each face, there is a square of side 3 that has no paint on it. So if you think about it, there is actually a cube of side 3 that has no paint on it. It is like the inner cube. If you strip away the outer layer of cubes, then the inner layer has no paint on it. And the volume of that is basically 3 cube, which is equal to 27. So that is the number of cubes that have no paint on them at all. Now question 2. Let's look at question 2 on the next page so that we have more. Now let's look at the second question. Second question says, how many of the smaller cubes have exactly one face painted? Again, let's first look at a side. So this is a side, this is the face of side 5. If you're looking at exactly one face painted, you're asking about those cubes that are in this region, inside this region. These will have exactly one face painted. All the other cubes, the ones that lie here, would have 2 faces painted because they're on the edges. The ones that are in the corners will have 3 faces painted, right, because they're on the corners. So they have the side that you can see, they have one on this side and they'll have one below. Same for this, you can see one on this side and one below that's painted. Ditto for this. The ones on the edges, there'll be one that you can see here and there'll be one on just behind it that is also painted. But the ones within this square are the ones that have only one face painted. So we already know the square is of side 3. So in this face, just on this face, there are 3 into 3, 9 cubes that have one face painted. Now there are totally 6 faces. So 6 faces, 9 cubes per face. So totally equal to 6 into 9, and that is 54, which is your answer. So that is the second question. Okay, third question. How many of the smaller cubes have exactly 2 faces painted? Brilliant, because we just discussed this, that if you look at one face, the ones along the edges, excluding the corners, are the ones that have 2 faces painted, right? So if you look at the face that is facing us, then you have 3 plus 3 6 plus 3 9 plus 3 12. Similarly, you'll have 12 more on the opposite face, right? We are basically counting the edges excluding the corners of the cubes. That's what they're making us do. So we have counted the face that is facing us, the face that is exactly opposite us. Now we need to count the edges that are joining the 2 faces. And that is going to give us another 12. So it's going to be 12 plus 12 plus 12, 36. And finally the last question. How many of the smaller cubes have exactly 3 faces painted? So now we are just being asked for the number of corners. And a cube has 8 corners. So the answer is D, 8. So finally, to summarize, all cube questions are going to require very strong 3D visualization. It helps to draw a very good diagram that helps with the visualization part. If you're not good at 3D visualization, then cube questions are going to take time for you. So it should be a question that you prioritize later towards the end of the test when you've finished other questions. Putting symbols or numbers on the sides of the cubes, this is a type of question we didn't cover, but it's just a simple variation. Instead of paint, if you put a number, for example, if there's a cube and on each face you put some numbers, 6, 2, 1, 3. This is what are called dice problems, but the principle of solving doesn't really change. This is the same thing. All you need to do is draw the diagram cleanly and you should be able to solve it. Alright, so this is Vivek from ExamVictor. Thanks for watching.